Hello everyone, welcome to this lecture of two-phase flow. My name is Mingchang Li. I'm currently a faculty at the Department of Power Mechanical Engineering in National Tsinghua University. Per the request from the university, I'm recording and sharing this series of lecturing for NTHE OpenCourseware. The topic for today's lecture is an introduction to the models for critical heat flux, the Leidenfrost point, and the film boiling. Please also be noted that the main content for this lecture is from the reference book written by Professor Van Carey. Here, let's take a quick look again on the boiling curve when the temperature of the heated surface is controlled. Note that there are 2 points on the transition boiling segment corresponding to the maximum and the minimum values of heat flux, respectively. The point for the maximum heat flux is also called the critical heat flux, and the point for the minimum heat flux is also termed as the Leidenfrost point. Also noted that in the temperature control mode, the transition boiling regime can be observed. The transport phenomena in this region is actually pretty interesting. The heated surface is covered by separated vapor film patches rather than a complete vapor film as in the Leidenfrost point. This allows liquid to be brought in contact with the heated surface at some locations. Consequently, the heat flux is increased with decreasing the excess temperature until the maximum heat flux condition is reached. The black arrows on this figure indicate the heating and cooling paths for pool boiling when the heat flux of the heating element is controlled. Note that the transition boiling mark with dashed lines here is unavailable in the heat flux control mode. However, the maximum and minimum heat flux conditions are still presented. For the case of water at 1 atm, on the heating curve, the excess temperature will jump directly from 30 to more than 1000 degrees C if the heat flux is increased slightly above the critical heat flux point on this figure. This leads to the possible melting of most materials in engineering applications or thermal damage of common devices. If the heating element or the hot device can sustain with this high temperature, the condition will directly change from nuclear boiling to film boiling. For the case of a cooling curve, if the heat flux of the heating element is reduced below the value corresponds to the minimum heat flux, the heat transfer condition will transform directly from film boiling to condition near to the onset of nucleation boiling. In other words, only isolated bubbles will present on the heated surface. No vapor columns or slugs will be observed soon after the heat flux is reduced from the minimum point of heat flux. In this lecture, we are going to investigate some models for analyzing the heat transfer on these two important points. A number of possible mechanisms have been proposed for the critical heat flux condition. First mechanism postulated that the vapor blanket begins to form when the vapor velocity is sufficiently high to carry the liquid away before it could reach the heated surface. The second mechanism states that the nucleation density is increased rapidly as the wall superheat is increased. Since the number and size of bubbles are increased correspondingly, the vapor blanket starts to form with packed and connected vapor bubbles right on the heated surface. The third possible mechanism is associated with the homogeneous interfacial instability on the interface between vapor columns and the surrounding liquid. If vapor columns and jets above the heated surface are sufficiently distorted to be laterally connected, the paths for liquid flow towards the heated surface will be blocked. This in turn causes the formation of vapor columns over the solid surface. The last mechanism introduced here proposed that in the final stage of nucleate boiling with high heat flux or high surface temperature, large vapor bubbles are fed with a number of small vapor jets. These jets carry vapor through a thin layer of liquid film under the big bubble. The thickness of this liquid film is assumed to be thin enough so that it is stable. The bubble is therefore hovering over the heated surface with a thin layer of liquid and the vapor jets in between. The critical heat flux condition is reached when the liquid underneath this big bubble is completely evaporated before the bubble can escape from the surface. Here, let's consider the third mechanism that involves the analysis of instability of vapor columns above the heated surface. It is postulated that the maximum heat flux condition is attained when the interface of the large vapor columns leaving the surface become unstable. The vapor columns are assumed to be located on the hot surface in a rectangular array as shown on this figure. The vapor-to-liquid interface is subjected to the analysis of Taylor instability of a semi-infinite liquid above a layer of vapor. The centerline spacing of the columns corresponds to lambda d. Consequently, the column diameter is assumed to be lambda d over 2. Lambda d here is the most dangerous wavelength for interfacial instability. The critical velocity for the vertical vapor and the liquid flow is given by equation 62. Since the density of liquid is generally much greater than that of vapor, equation 62 can be simplified accordingly. Equation 64 is obtained by assuming all heat flux from the solid surface to the fluid is due to latent heat corresponds to these upwards vapor columns. Equation 65 is from the geometry showing on this figure. Finally, the expression for lambda d and the maximum heat flux can be obtained. Note that the coefficient 0.149 here for the flat plate surface is derived by Leonard and Deer. It is different from the original coefficient derived by Zuber, which is 0.131. This table summarizes some correlations on the basis of this model for a number of different hot surfaces. Note that in using this table and correlations, the reference maximum heat flux is chosen to be the value calculated from using Zuber's original model. The capillary length scale is used here for evaluating the applicable range in terms of the size of the heated surface. For the minimum heat flux point on the cooling curve, Zuber argued that it occurs when vapor is not produced rapidly enough to compensate the collapse of the vapor film. Here is a schematic illustration to the cycle of vapor bubble formation and collapse or release on the heated surface. The video also illustrates the scenario corresponds to the cyclic motion in the normal direction of the liquid-vapor interface as described in the figures. Since this is a typical case that the fluid with a higher density sits above the fluid with lower density, it is reasonable to apply the Taylor instability analysis on the liquid-vapor interface. One cycle here is defined as the center of the vapor film moves from its lowest point to the highest point. If the heat transfer in this condition is assumed to be equal to the energy released by the bubble departed from the surface, the minimum heat flux can be defined as the product of energy per bubble and the number of bubbles released per unit area per unit time. From the Taylor instability analysis, The most dangerous wavelength and the corresponding frequency can be determined. The energy carried with each bubble is the latent heat corresponds to the formation of it. According to this schematic illustration, the number of bubbles released in each cycle is 2. With these values, an expression for the minimum heat flux can be derived with an empirical coefficient C. In the film boiling regime, the entire solid surface is covered with a continuous vapor film. For the case of vertically placed hot plate in a saturated liquid, a standard boundary layer analysis can be applied for deriving solutions to the temperature and velocity profiles in the vapor film. The heat transfer rate can also be obtained with the resulting temperature profile. The continuity equation in the vapor and the liquid phases correspond to an incompressible fluid, which is an assumption. The momentum equation in the vapor film is simplified with dimensional analysis. The buoyancy effect is included. In the liquid phase, pressure gradient and the gravity term are assumed to be self-balanced and are neglected from the equation. Energy equation is only needed for the vapor film since the liquid region is assumed to be at saturation temperature. By inspecting these partial differential equations, the number of boundary conditions required for U, V, and T are determined. Here is a set of the boundary conditions corresponding to this problem. Most of these boundary conditions are obvious and straightforward. These two red boxes indicate two boundary conditions that are relatively special. The first one up here is used to fulfill the requirement of 4 boundary conditions in total for UV and UL in y direction. The physical meaning is that on the vapor to liquid interface, the shear stress is balanced, so no slip on the interface. The lower one corresponds to the boundary condition required for VL in y direction. It is derived from a mass conservation on the unit control volume contains the interface as shown in this figure. Notice that the liquid to vapor phase change is also introduced to the analysis with this important boundary condition or interfacial condition. The solution of this problem can be derived by performing a standard boundary layer analysis. The string function is used to include U and V and take care of the continuity equation. A similarity variable eta is used to convert the partial differential equations to ordinary differential equations. Figure 24 shows the results for velocity profile and temperature profile. The Leidenfrost phenomena refers to the film boiling of small liquid droplet on a highly superheated surface. The liquid droplet vaporizes very rapidly, so that the production of vapor on the side of the droplet facing the hot surface establishes a pressurized vapor film that repels the liquid droplet away from the surface. In this video, the liquid droplet is supported by this thin vapor film in between the droplet and the hot surface. The droplet is hovering over the surface due to the vapor flow resulted from vaporization. In this case, heat is transferred from the hot surface to the droplet by conduction and radiation through the vapor film. The Leidenfrost phenomena in technological applications such as spray cooling is very important, since in this case, the impinging liquid undergoes film boiling directly. There are two important issues regarding the Leidenfrost phenomena. The first one is the threshold minimum superheated surface temperature, or the minimum heat flux, at which the droplet is supported stably with the vapor that undergoes continuous film boiling. The The second one of interest is the heat transfer rate under this condition. This figure shows an idealized model for analyzing the Leidenfrost vaporization. The continuity and momentum equations correspond to the disk of the vapor film underneath the droplet. The vapor is treated as an incompressible fluid. The heat transfer from the hot surface to the droplet by conduction through the vapor film balances the evaporation rate of the liquid droplet. Boundary conditions are listed here for reference. By using integral method, a solution to the thickness of the film delta can be determined. The convective heat transfer coefficient is defined by taking the thermal conductivity of vapor film divided by delta. By using this convective heat transfer coefficient and the temperature differences between the hot surface and the droplet, and perform thermal energy balance of the vaporization process until the liquid droplet vaporizes completely, the time duration for the Leidenfrost vaporization can be obtained. In general, the value of TV can be measured from experiment and to be compared with the analytical solution. This information can then be used to modify the evaluation of the effective heat transfer coefficient across the film. In previous lectures, we have introduced the concept of disjoining pressure. This is resulted from the attractive forces between the liquid molecules and the molecules of the solid surface. This disjoining pressure difference can significantly affect the heat transfer for ultra-thin film vaporization, like the case shown on Figure 9 here. Due to the disjoining pressure difference, the pressure at the interface of the liquid film to vapor at location B, which is PLI, is different from that at location A, PLO. Noted that by sign convention, if the affinity of the liquid for the solid draws liquid into the film, PD is taken to be negative. The result is that if the liquid film is thin enough, the ultra-thin film can be superheated and be at equilibrium with the vapor. The liquid film may not necessarily be completely evaporated, even if its temperature is raised above its normal saturation temperature. This means that an equilibrium thin layer of liquid film with thickness delta may remain on the surface. Figure 12 shows an example on the difference of equilibrium vapor pressure versus the saturation pressure with respect to the liquid film thickness. It can be seen that the disjoining pressure effect decreases rapidly with increasing the film thickness, which can also be seen from inspecting equation 84. The significance of this disjoining pressure effect on thin film evaporation and condensation can be illustrated with Figure 13. To vaporize the liquid in the equilibrium thin film region, which is superheated due to the disjoining pressure effect, the wall temperature must be raised above equilibrium liquid temperature allowable for this ultra-thin film. More details about the disjoining pressure can be found in Chapter 3 of the textbook. Here is a summary of this lecture. We discussed about the possible mechanisms and representative models for the critical heat flux and the minimum heat flux conditions, which are both affected by the instability of the vapor to liquid interfaces during the boiling or cooling processes. Then we showed a theoretical approach for analyzing the film boiling. It is similar to a boundary layer analysis. The Leidenfrost phenomena corresponds to the evaporation of a liquid droplet on a highly superheated surface. there is a stable vapor film in between the liquid droplet and the hot surface. A theoretical analysis was also introduced. Finally, we briefly discussed about the effect of disjoining pressure on the evaporation of ultra-thin liquid film.